So, because speaking on that, we do have one more official lecture following this one. We do have the next lecture is going to cover chapter 30 as well. But then following that, over the break, I'm going to be making extra lectures. They're not going to be worth anything. I don't even know if I will have. I might not even go through all the whiteboard solutions and some of those problems unless like they're some of those are a little bit cool. Like there's the calculate how long you have aged because you rode around in an airplane or something like that. But those are not included in the course this go around because we're under a little bit of a time constraint and we still want to get all the important good stuff. But I do think it is still kind of like a very, very nice conclusion to everything. It's the climax as we've built up to everything since the electric force. Since we first started talking about the Coulomb force, it all kind of leads into our discussion of relativity and the speed of light and stuff like that. So it's a cool thing, and I will make those lectures over Thanksgiving break, but they're not going to be any part of the real course. If they are of interest to you, you're welcome to watch them anytime as they come out over break, or you still have access to the Canvas course after the semester ends. But in any sense, it'll be all sort of stuff like that. As for questions on the last lecture covered on the final will be Friday. So it'll be the last of the material that we've got. I don't have any special bonus lectures that are just for the fun of it, besides those extra ones. Not any in-person lectures like this, just for the fun of it. So Friday will be the last one that we've got, but I imagine I will be in frequent office hours, both over break and throughout finals week. So for anybody that needs me for any of that stuff, I will be all over the place. So let's talk about the topic for the day. So part of what we're seeing here, chapter 29 was all about the magnetic field and the magnetic force, how first a moving charge creates a magnetic field, and then how a magnetic field could be used to move around a charge. And that's great, that moves some things around and everything else, but we saw that the force only acts on moving charges in the first place, which was a little bit, okay, that's, not quite the same as the electric force, but whatever. Things are just weird sometimes like that. But we went through all of that stuff and we saw, okay, well, we can do all of this stuff with the magnetic field. We understand how the magnetic field can be produced. Now the question is, can a magnetic field make the charge move? Does the charge have to be moving for it to experience a magnetic force? Or is there some sort of way that we could have a magnetic field that actually creates that current or that movement of charge rather than the other way around? And we kind of know that we can do this, right? Because of course, if it creates a force, then it should be able to move some charges around, but we need to pick apart exactly how that's going to work. And that's what today is all about. So, the way this happens is the current is present when there is a change of flux. With a bunch of observations that we might have, especially going through, there is a lab associated with today's lecture. It's a short little lab all about inducting currents and other things like that. But going through that and going through some of the stuff from today, what we really end up with here is that if I have a change of flux, I create a potential difference in a loop. So if I've got some sort of wire or something like that, or like something like this is perfect, right? A loop of wire or anything else, I would want to make sure that I would have both ends connected. So it's a complete loop, right? Not just some sort of open circuit. Hopefully I'm not destroying my USB cable like this, but if it's a closed loop all the way around, then I would be able to create a potential difference within that loop by changing the magnetic flux going through it. And we need to pull back a little bit and think, okay, flux, it's been a little while. We talked about Gauss's law at some point, but it's been some time since we've looked at that. So we do need to talk about that, and we will in just a second here. But once we know what that induced potential would be, we could calculate out an induced current. That is the value that a magnetic field can create a moving charge. But notice here that we're not just moving charge out of nothing. Something is changing to make this happen, right? A uniform magnetic field would not necessarily do this on its own. But if I start to change that field, then comes the possibility of kicking in some energy to some of these charges to get them moving. So, magnetic flux works a whole lot like the electric flux does. In fact, flux is something that is more general. It's not just applied to these two fields in particular. Flux is anytime I have a field passing through a surface area. So then, everything that we might remember from electric flux, we just replace it with magnetic equivalents. So instead of the E field, it's the B field. And we can even do something cheeky and just be like, and there we have it. Now it's magnetic, right? That doesn't look very good though. But anyways, we could just take everything that we know from electric flux and apply it to magnetic flux in the exact same way. So a quick little review here. We might remember this slide. If we are measuring this, it does come out to be this kind of nasty integral, right? Where we're saying, okay, B.dA for how much of the magnetic field is passing through every point of the area. And specifically passing through, and that's determined by our dot product here, right? Because if I had a magnetic field going like this over the surface, that's not passing through the surface. There's no flux contributed from that field. It is only what we see actually passing through. That's what counts. So there will be times where we have to deal with the full integral definition of this, but oftentimes, if you remember, we tried to look at easier cases. Cases that were a lot more simple. If we have a uniform magnetic field, and also the area is flat, that makes this entire thing easier, because now we can look at this integral and we can say, hey, B is a constant for all of space, that's fine. dA, being the only thing left in the integral, is just the area. And then this definition in particular is fantastic. That the flux is equal to B dot A, wonderful. Very easy to use. But you might also, if you already know what the angle between these two is, the cosine of theta definition works very well as well. But in any case, what we're looking at here is we're looking at some sort of dot product, whether we have it tilted, whether we have it completely perpendicular to the, and I'm talking about the surface area, perpendicular to the field lines. A and B would be parallel. Our dot product definition does wonders. So, when we're talking about this, and I'm going to come back to this, nature hates change, or specifically, nature opposes change when we're talking about magnetic flux. I'm going to come back to this idea again in just a minute here. But what we're looking at here is that anytime we start to change the flux, that's when we create an induced potential. And there's a handful of different ways that we could actually change that flux. Perhaps B dot A, that's changing. Maybe the angle between those two is changing. Perhaps the magnitude of B can change. Or maybe the direction, covered in B and A changing, but a direction, a magnitude, the size of the area, how much of the area experiences the magnetic field. All of these are different possibilities for what we could have that would change the flux going through the loop. And as soon as we start to change that flux, we are going to create an induced potential difference. So, I want to try this out at a problem. And I've got a little bit of a label here to see if this helps at all. So I'm going to be calling these things sometimes B external, because I think that makes a little bit more sense. But then we're also going to see later an induced B field. And I'll talk about that in a minute. But for now, let's assume we have some coil of wires. So it's 1,000 loops, and there's a magnetic field coming out of the page, so perpendicular to the plane of the circle, but area and the B field are both parallel with each other. Those two vectors are parallel. Let's say that this diameter is 1 centimeter. Let's say that the magnetic field increases from 0.1 Tesla to 0.3 Tesla, and it does so in 10 milliseconds. What is the induced potential difference in the coil because of that change of flux? All right, so let's start taking a look here. Oh, no, not that. Certainly not that. I forgot to group those things together, and then I didn't fix it before the next go around. So, go ahead and throw this thing in here somewhere. So we'll need to be careful with this. Shrink it down just a little bit so it's manageable. All right, so we've got some details that are of interest here, right? We know that the diameter of this entire thing is supposed to be 1 centimeter. Is my pen doing weird things again? I've got a bad feeling it is. Yeah, man. Hang on. I just try to do this and to get it fixed because like my handwriting like really goes down the drain when it's not working properly. And my handwriting is already rough enough as is on this thing. So we know that the diameter is 1 centimeter, which means that the radius would be 0.005 meters. If we're interested in area, which is one of the two parts of flux, we would say, okay, well then that's just pi r squared. Perfect. Golden. Now, I've got some other details that are of interest, right? I know that my B field goes from 0.1 Tesla to 0.3 Tesla, but it does so in a span of, let me make sure I'm not screwing up this time, 10 milliseconds. 0.01 seconds. Okay, so that's all information that we can use. Right now, if I'm thinking about flux, well, these two are, the field is passing right through, right? The area vector and the B field vector, they're pointing parallel to each other, so the dot product goes away, so I could just write out my flux this time around as B times A. Perfect. Now, I run into a little bit of an issue, right? Because now what I need to do is I need to actually take the derivative of this. I need to say curly E is equal to, and I'm just going to say the absolute value for now. We'll talk about that direction in a little bit. d phi dt. So piece by piece, if I actually think about what this could mean, I could say, okay, well, d dt of B times A. And then I look at this thing and I say, okay, is my area changing at all? No. Is my angle between these two things changing at all? No. So this is nice and easy. I can just pull out that area. And what's left, we know that the B field is changing, so that's the thing that actually gets the time derivative. Now, I look at this and I say, okay, well, this is great, but that's a derivative, and this is two numbers, right? But we remember that if we're looking at averages or a linear transformation, and for now, let's just do that. If we assume it's kind of a constant ready change over the course of this thing, then we can replace dB dt with delta B delta t. And now that is something that we can manage because we have delta B as our 0.2 Tesla, our delta t as 0.01 seconds. But here's an issue. I've missed something. I've neglected something here. There's some variable that I didn't use here. What am I missing? Chat, what do we think? What have I failed to take into account? There's loops. And it always comes back to loops. It always comes back to loops. There are 1,000 loops here. It's not just one loop, it's 1,000 loops. So even though I might find the potential difference from one loop, oh, there goes the pen again. Come on. These problems have just gotten so much worse. I could say from one loop, the potential difference from one loop might be, I can plug all of these numbers in and I would find 0.0151 volts. But I have 1,000 of these things. My flux is not just B times A, it's B times A times N. B times A times N. A dB dt times N. The full thing requires me to take into account that every single one of these loops has the same flux and the same change of flux going through it all together at once. So when I plug that final answer in at the end, I'm going to take this potential difference from one loop. And now we should see, what is that decimal exactly? 1.571 volts. So not 1.7. Perfect. That's not very good. 1.571 volts for the entire thing all together. So how are we feeling? Do we have any questions on this one, or are we feeling all right so far? Barely alive is still alive. It should be in there somewhere. It depends on where you round from pi, I think. But that's what we've got. So, let's go ahead and keep moving right along. So how do we actually think about the direction of this? That's another trick. What's going on with that? Well, we actually have a different law to describe that. And this is where my phrase, nature hates change, like really comes into play. Right? If it was just about the fact that it's a change of flux that creates the potential difference, then I would just say that. I think that's a little bit easier. But nature hates change is a little bit more punchy, I think. But also, it really tells us about what direction things need to be going. See, what happens here, and when we're talking about induced potential and induced current, keep in mind that a loop of current creates a magnetic field. So this change of flux will end up creating another magnetic field. And I'm going to call that the induced magnetic field. And so that's why I'm specifying that there's this external magnetic field, the external magnetic field actually acting on our loop, and then what the loop produces in response to that is the induced magnetic field. But this is where it really comes in of where we're going to try and oppose change. Anytime we have a change of flux, the potential, the current, the field induced, created by that response is going to be to try to maintain the flux that we already have. That means if I have my loop, let me actually try and keep this all in one hand together. If I have a loop of wire, and I have a magnetic field going up through the bottom of this loop, there's currently a magnetic flux through this thing. If the strength of that magnetic field increases, if the flux gets larger, the loop says, I don't like that. I hate that change, and I wanted to see the flux exactly where it was from before. So what it's going to do is it's going to induce a magnetic field pointing in the opposite direction to try and maintain that flux. And then, of course, as time goes on, it loses that battle, right? But this is actually some of the issues when we're talking about like transferring a lot of current very suddenly and everything else. And this is kind of like a natural limit, how much current you can move through different systems, because quite literally, the currents oppose moving currents. It doesn't like to see changes in things that are there. If there's already a current there, or if there's already a flux there, it's not a big deal. It's when there's a change to that flux That's what makes the difference. So in the opposite direction, though, let's say I've got the exact same scenario again. I've got a loop, I've got a magnetic field coming up from the bottom. But let's say the magnetic field starts to get weaker. It starts to decrease in magnitude. The loop says, hey, I was perfectly happy with the flux that I had. I don't want to lose that flux. So it's going to create another induced field pointing in the same direction as the external field to try and maintain that flux. So for example here, if we're looking at the problem that we just solved, what we saw, and I don't even need to worry about any of our equations that we just dealt with, but what we're seeing here is that the flux is coming more out of the page. The magnetic field was already coming out of the page, but it's getting stronger. So flux doesn't technically have a direction, but I think it's a little bit easier if we think about it that it does. There was flux coming out of the page, and it was getting stronger coming out of the page. So to oppose that, the induced magnetic field opposes that change. It goes into the page instead. So I'll write B induced. And what direction does the current have to be going to create that magnetic field? Well, it's just a loop. So we can take our right-hand rule to find that. If the magnetic field needs to go with my thumb, then the current wraps around as my fingers do. So if it's going into the page, then I should expect to see an induced current going clockwise. But that's what Lenz's law is trying to tell us. It's trying to tell us, okay, well, if you use Faraday's law to find what that potential difference would be, Lenz's law is telling you what direction the current induced would be going. So, let's try this. And this is a little bit different. The magnetic field is no longer changing, but the loop is. Because what's going on in this problem right here is you can see not all of my loop is actually contained inside. It doesn't all have magnetic flux passing through it currently. It doesn't have magnetic field going uniform over the entire thing, only part of it. This part out here has nothing. So, with that in mind, let's imagine this scenario. I've got a 0.2 Tesla magnetic field, and I've got a loop that is traveling into this magnetic field at a rate of 50 meters per second. The total resistance of the loop is 0.1 ohm. What are the magnitude and direction of the current in this loop? All right, I'm thinking we should start taking a look here. So let's go ahead and snag this picture. Let me say some words so that when I try to write on this thing, it's not going to work. Right? Something about being able to immediately draw out. Oh, that's still the wrong thing. Whoops. Something about immediate. Ah, and it does work. Okay. Well, as soon as I need it to, it'll probably fail on me, but that's okay. So here's what we've got, right? The way that I want to approach this thing is I want to start with, again, my definition of what the magnetic flux would actually be. But this kind of comes with a little bit of a caveat, right? So I'm just going to write out the basic kind of thing here. As last time, they're perpendicular. The field is coming right through, so the dot product is not a worry or anything else like that. But what do I mean by area here? I don't just mean the entire area of the loop, and that's not a quantity that I could calculate anyways, right? Because what's the length of this thing? I don't know. But what we're really seeing here is that there's this cutoff point. As we've got it drawn in our picture here, the magnetic field is only passing through part of this thing. And so the flux is really only what's going on in this region. Down here, there's no flux. There's no magnetic field, so there's no flux. So we have to keep that in mind as we're looking at this thing. And, well, what I'm going to see now is, okay, well, that's a rectangle or a square or however you want to call it. So what I'll say is this is B times length times width. Now, with something like this, I don't know what length is. Width, I can see that's 5 centimeters, but length, I don't have a quantity of. But let's forget about that for a minute. Let's not worry too much. We're not after the flux. We're after the change of flux. So let me take that derivative. Let me say, okay, if I were to take the time derivative of flux, where does that hit? What pieces will it actually hit? Well, my field is unchanging, right? The field that's actually here is not going to be changing at all with time. The width of my wire is certainly not changing, but the length, that actually is. If we imagine that this whole thing has moved up a little bit more, right? It gets shifted up so that we get something, so we have to kind of imagine here, but let's imagine we look like a moment later, then the field lines would be at this point. And we would now have had an increase in the total length of the circuit that is now inside the magnetic field. And I bring that up because now as we're looking at this thing, we say, okay, well, those pieces come out that were constant, but the length as it's changing, the length of the loop that's actually inside of the magnetic field is changing. That is a time derivative of a distance. A time derivative of a distance is a velocity. This 50 meters per second tells us that if we were to wait 1 second, the length inside of my magnetic field now would be 50 meters. Or the extra length, the change of length would be 50 meters. We do run into a little bit of an issue because if we look at this picture, it's clearly not 50 meters long, right? It's probably more like 10, but that's not important because what is important is that rate of change. Maybe this doesn't work 1 second down the line, but in this moment in time, we can use this definition. So this becomes BWV, which is equal to our induced potential. And when we plug that all in together, what we should find for that value is a potential difference of 0.5 volts. So then when I say that the resistance of this circuit is just 0.1 ohms, then my induced current should be 5 amps. Now, I actually don't want to box that in yet, though. Because now the question comes, okay, well, that's great. What direction is it going? So let me think about this again. Let me go back to my description here when I was talking about the what does it look like a moment from now? Where does the field line up now? The field, now having taken this increase in area, I've got 4 more field lines inside of this loop than I had a moment ago, right? The magnetic flux is getting more and more out of the page. As time goes on, that's the direction that we're going. We're getting more and more out of the page with that magnetic flux. And so my loop is going to oppose that. My loop says, no, I was perfectly happy with the amount of flux coming out of the page that I already had. And if you're going to try and increase that, I'm going to induce a magnetic field that goes in the opposite direction. And I'm drawing it all the way throughout the loop. Because what we've got going on here is that the current is not moving through half of the loop. The current's moving through the whole loop. So the induced magnetic field is in the whole loop. But all of it's going that way, right? So if I'm using right-hand rule, I say, okay, it's going into the page. My fingers wrap around. I should be expecting to see this induced current going clockwise. And there we have it. We don't have to change the field. You only have to change the flux. Changing the field is one way to change the flux, but it's not the only way. You can alter the area or you can change the angle between those two as well. A really basic AC generator has a constant magnetic field and it spins a loop around so that the angle is constantly changing. There's a constant change in the flux. That's one way to generate electricity. Yeah. That's exactly what's going on with an alternator. Well, the alternator, I take that back. An alternator is a little bit different because in the case of the alternator, that's backwards. It's a magnet on the inside spinning around, and the coil of wires is around it. But it's doing the same thing, right? It's changing the flux through the coils. So, in this problem, I have 3 different loops. They're all the same loop, same size, same resistance, but they're all 3 in different layouts with different fields. So the B fields are in blue here, but within each picture, what is the magnitude and direction of the induced current? All right, so let's start taking a look here. Let me snag these pictures. Give ourselves a little bit of good space here. All right, I'm actually going to start with part C here because this is the easiest one to do. What is the flux going through loop C right now? What do we think, chat? Zero. The field lines are not passing through the loop. They're passing right on by, right? Here's my loop. Here's my field line. Goes right on by, not through. Flux is 0. If I ramp up my magnetic field, it's still going right on by. It's still not passing through the loop. Current is equal to 0, no flux. And that's the end of that one. So now let's focus on A and B. Okay. So as I'm going to handle this thing, what I'm going to say is same approach as before. Think about the flux first. B, and now we're perpendicular again, right? Or the plane of the loop is perpendicular again. So it's B dot A just comes into B times A. Again, though, I don't really care about this. I don't know what the magnetic field starts as. I don't know what it ends as. I just know what it changes like. So if I take that time derivative, I say, okay, well, if I'm taking this time derivative, what actually changes? The area is certainly not changing, but the magnetic field is, and they tell us what that rate of change is. So this is A dB dt. Okay, well, I know that the area of each loop, these are all circles, so this is pi r squared is equal to my area. I know that each of these has a resistance of 0.2 ohms. I know that it has a diameter of 10 centimeters. So what I can do then is I can say that the potential induced in here would be a pi r squared times dB dt, and dB dt is given. It's 0.5 Tesla per second. So then, we can find that value. If we plug in for that, then we should find that the potential difference, or the induced potential, is 3.93 times 10 to the negative third. Then we can say, fantastic, well then the induced current is equal to the induced potential divided by that resistance. We should find 19.6 milliamps as our induced current in each case. And I say in each case because let's look at this thing. Loop A and B, they have the same rate of change, albeit off by a negative sign, the same area, the same resistance. All of these quantities that we plug in are exactly the same. Both of them have the same induced potential. Both of them have the same induced current. It's the direction that might be different. So now we need to look at these on a case-by-case basis on thinking about that direction. So what I'm going to say, okay, for loop A here, it is increasing. The flux is going into the page, and it's increasing. So our induced magnetic field opposes that change. It wants to come this way, out of the page. B induced coming out of the page, what current would create that? If I align my thumb like this coming out of the page, my fingers wrap around this direction, I expect to find a counterclockwise current. Just like that. Now, let's look at loop B. B is decreasing at a rate of 0.5 Tesla per second. So the flux was coming out of the page towards us, but it's becoming less and less and less. So our loop says, hey, I want to hold on to that same flux that I already have. So again, we're actually going to create the same direction of an induced magnetic field. That induced magnetic field still goes in the same way, still needs the same induced current. Going counterclockwise. So the direction of the magnetic field before, let me say that again. The direction of the magnetic field as it's currently traveling does not matter. It's the direction of the change that indicates what the induced field is going to try to do. C does have an area, but we have to think about the vectors. If we take the approach of what the flux actually is, it's not just B times A. I'm simplifying it to B times A. But we have a uniform field and a flat surface, so technically the flux is B dot A. And the area vector always points out perpendicular to the surface itself. So we would expect the area vector to go this way, but then area and the B field are perpendicular to each other, so it's 0. Yep, A is the area. Yeah, so it's not that the B field or the area are actually 0, it's that the angle between them makes their dot product 0. This. So what I've got here is a 100-turn coil is set up in such a way, the wording's a little bit strange here. A 100-turn coil is set up in such a way so that it's essentially flat, laying on the ground, vertical axis pokes directly through it, going up. A uniform magnetic field has an angle 60 degrees off from the vertical axis. So step 1 is to draw a good picture here. Maybe 2. That magnetic field increases from 0.5 Tesla to 1.5 Tesla in a span of 0.6 seconds. What is the induced current in the loop? What is the direction of the current if we were to look from a top-down view? This is a perfect opportunity to think about what's going on with that dot product and to take that real definition here. Right? Thinking about what's going on this slide right here. So, with that in mind, go ahead and work on this one. Okay, let's start taking a look here. So, we don't have a picture to go off of, which makes this thing a little bit trickier to look at first, but we can come up with a pretty good one here. Let's imagine a lot of our coils are usually out of copper, so I'm going to draw this thing in orange. So here is like my bundle of coils, and I'm taking a side profile view. And here's like a bunch of, try and make this look like it's a bunch of wires, actually. Let me do, ooh, I've got artist tricks, don't I? Artist tricks like that. And now I can scribble across to my heart's content. So this kind of looks like a bunch of coils, right? A bunch of wires going all the way across the thing. So that is my bundle of coils, and that means that when we're thinking about what is the vertical axis that we hear so much about here, it's pointing directly up like this. And let's go ahead and make this a dotted line so that we can kind of see It's not a physical thing, it's just where we're imagining our vertical axis to be. So again, kind of my orientation here, if we've got something going on, a visual aid to help us, this is what I'm kind of imagining. Here's my coil of wires, here's my vertical axis sticking directly up through it. So I know that my coil of wires has, let me make sure that I'm actually drawing and not just erasing. This is 100 turns with a total resistance, I think, of 0.1 ohms. Is that right? 0.1 ohms. Okay, so we're also told about the magnetic field point 60 degrees away from the vertical axis. So that means that my angle is going to show up kind of like this. That's about 60 degrees or so. Kind of like this, trying to make these as parallel as possible. But again, I'm a physicist, not an artist. So if there's a little bit of inaccuracy here, try not to hold it against me. But this is what our B field looks like, our external B field. And then it's creating this angle, 60 degrees. But this is actually the angle that I want, right? I don't actually care about, I know there's a 30-degree angle between the plane of this thing, but that's not what I care about, because if we think about what direction does the area vector go, what direction is that pointing in? The area vector should be pointing perpendicularly away from the plane of the coils. So in a right angle right there, there is my A vector. Magnitude of which? Pi r squared. So that's why I'm interested in my 60-degree angle here, because as I'm looking at this thing, if I'm thinking about my flux, I do need to take my dot product definition. B dot A. I can't just say B times A here because there is an angle between these two and it's not just 0. But I can simplify this because I already know what this angle should look like. I can say, hey, this is B A cosine of 60. And that makes that whole thing a little bit easier to handle. So once we're here, again, I say I don't really care what's happening with either of these things. I really care about the change of this flux. So let's take that derivative and we look at this piece by piece and we say, okay, great. What parts are actually changing? Area vector, that's a constant. Cosine of 60, that's a constant, right? The orientation of either of these is not changing. Let me finish writing out this part first. So I say, okay, A cosine of 60 comes out because those are both constants. But the B field is changing in magnitude, so that gets caught. So then, how is that changing in magnitude? Well, there is a constant increase from 0.15 to 1.5 Tesla over a span of 0.6 seconds. So what I can say is my same argument as before. That's just a derivative. So I could rewrite that as delta B over delta T. And in doing so, then I can say, hey, delta B is 1 Tesla. Delta T is 0.6 seconds. Pi r squared, fantastic, but I made the same mistake again that I did before. What did I miss? What do we think, chat? Loops indeed. There are 100 turns to this stupid thing, so I can't just settle with that. I have to say times n. Times, oh, I don't have a lot of room there. Times n. N is a constant. N is not changing. I am not adding more loops as we're doing this experiment. The coil is set in stone. Well, metaphorically speaking here, it's actually made out of metal. But I need to multiply all of these values by n because each loop is experiencing the same change in flux, this same flux that we have coming into it. So at the end of the day, when I plug all of that stuff in, my final potential, n a cosine of 60 times dB, whoops, not dB, delta B, delta T. What I should find is that my final potential should be, where did I have this written down? 0.0262. Oh. Sometimes I don't know what my hand does. 0.0262 volts to find my induced current. E divided by R. I should end up with 0.262 amps. Fantastic. So now that I have this, now I need to think about that direction. So let me take another view of this thing. Let me imagine a top-down view here. And I'm going to try and do something again where I make it look like I've got a bunch of loops all together at once. That kind of looks like a sloppy coil. Something like that, right? Something almost circular, I guess. A whole bunch of these wrapped around each other. But I'm seeing my top-down view. But let me think about it like this. When we're taking a dot product, what we're really doing is we're taking the components of each vector that line up. So if I imagine for a second that this is a y-axis, and maybe this axis right here is an x-axis, my B field has y and x components. But the x components aren't going through the loop. They're just skating right on by the side. It's the y component that actually matters. What is the y component of my B field? Why, it's B cosine of 60 degrees, or B sine of 30 degrees, right? Those are equivalent values. So then what I'm going to do here is I'm going to say, hey, this is my y-axis, this is my x-axis, my B field as it's coming. I'm only actually going to focus on the y component of my external B field. So I'll say B of y goes like this, where B of y is equal to B sine of 30. But it's only focused on the direction that's actually passing through the loop. That's the only part that I'm actually going to care about here. So if I see my B field is increasing, my flux coming towards me is increasing, my loop says, not today, and tries to induce a magnetic field going in the opposite direction. Going into the page, so I use my right-hand rule. My thumb goes into the page, my fingers wrap around in the direction of current, and we should find an induced current going clockwise. And there we have it. So, I think that's all I've got for the day. We've got one more lecture after this, which is kind of crazy. But we close out 30-1 with that.